This presentation is going to go through the design process for Flexure for prestressed concrete members. By the end of this presentation, I want you to be able to use a given design aid to determine appropriate section types and preliminary sizes, describe the concept of Kern points and explain how Kern points are affected by allowing or disallowing tensile stresses, use a given procedure to design a prestressed concrete beam for Flexure, and finally, calculate composite section properties and use them appropriately in the design process. During the design process, the designer must choose a cross-section type, material types and properties, tendon profiles, the pre-stressing force and total amount of pre-stressing, and also the area of our reinforcement, our non-pre-stress reinforcement. So design compared to analysis. Design, we're typically given some general parameters about our structure, so maybe span length, loading, and type of structure, so purpose. And we need to come up with our initial design, where in the analysis process, we have a given cross-section, a given beam, a given reinforcement, and we're analyzing the actual strength. So anyway, these are some of the things that we need to determine during the design process. Some of our preliminary or main design objectives are to meet our stress checks or our service limit state, meet our deflection checks, and also make sure that our structure has sufficient ultimate capacity. So we're going to see how to do these three throughout this presentation. There are several design tools that we're going to use in the design process. Two of the primary ones are design aids. So these design aids typically tell us cross sections that we can start with based on our span length and our loading. So this design aid's from Collins and Mitchell, and you can see we can come in and say, well, what's our span length and our given loading, and then determine a cross section that we would start with in our design process. Another design tool that we'll use is our Kern point analysis. Kern points, what this analysis will allow us to do is determine the maximum and minimum eccentricities that will allow us to meet our stress checks in a section. So here you can see in this section, if we have the centroid of our pre-stressing within this gray region, we would theoretically meet our stress checks. So we'll learn more about Kern point analysis in this presentation as well. Our cross-section type is going to be dictated by several things. First, the structural system, whether it's a building or a bridge, and also the construction sequence will help to guide us and help dictate what cross-sections we can use. Cross-sections are typically standardized, so there are standard sections that are available for buildings and also standard sections that are available for bridges. So whether you're designing a building or a bridge will dictate kind of what types of cross sections you'll use, and we'll look at some of these in this presentation. The type of cross section you can use is also dependent on the availability forms at your local precaster. So precasters will typically buy steel forms for these standardized shapes, and not all precasters will have the same sets of forms. So when you're in the initial design process, you need to check with some of your local precasters to see what standardized shapes the precasters can make. So next, the span to depth ratios. So with pre-stress compared to non-pre-stressed reinforced concrete members, there are different span to depth ratios that are typical. And there are also span to depth ratios that are appropriate for different types of members. So we'll look at some of those in later slides. And then also the magnitude of loading. So whether you just have building loading with or office, residential, or you're trying to carry a pool or parking. So there are a lot of different types of loadings for buildings, and then with bridges, there you have your vehicular loading and your truck loading. There's loads from trains, so a lot of different types and magnitudes of loading. And the type and magnitude of loading will also help to dictate what cross-section you can use. As I said, there are different standardized shapes that are available for buildings and bridges. And typically precasters will either focus on all building products or all bridge products. So you'll work with a different precaster depending on what type of shapes you're working on, or what type of structures you're working on. So with buildings, some of the primary ones are double T sections and hollow core, which is just a slab with these cylindrical voids running down the middle of it. And then some others are single T's and inverted T's. So these are four of the main standard shapes for buildings. For bridges, we have other shapes. So segmental box girder bridges, typically post-tensioned. We can have U-beams and curved U-beams that are pre-tensioned, precast. I-girders, box beams, and bulb T's. So these four are our main pre-tensioned elements, and the segmental box would be our main post-tensioned standard shape for bridges. And there are many available design aids. I'm going to look at or show you guys a couple of these in this video, but there are many that are available. So typically, if you search for design aids for a given section, you'll be able to find something. Shown here again are some of the standard precast section shapes for buildings. Again, the two most popular would be double T's and hollow core. Inverted T's are often used with some of these members. So double T's or hollow cores can frame into the inverted T's to create the structural system. Some L-beams are often used for exterior beams in a structure, and then again the beam would kind of frame in here on the ledge. And then two other members that can be used are rectangular beams and solid flat slabs. So on the next couple slides, I'm going to go through some of the different design aids that are available. The first one here is just a design aid taken from Collins and Mitchell's Prestressed Concrete Structures textbook. With this design aid, you can come in and choose your span length and your given loading, and then you can come and see an approximate structural shape for that span length and loading. So you can see here, with a 60-foot span and about an 80 pound per square foot service load, we would have a 32-inch deep double T section. So this, could be a starting point for our design if we had those parameters. So you can see, there are different span lengths and loadings that are appropriate for hollow core and longer spans for these single T sections. But again, this is just a design aid to give you some basic guidance as to what structural shape you should start with. Here are an additional two tables, design aids that are provided by Collins and Mitchell. So you can see the one on the left gives us some approximate values for eccentricity plus the top Kern point and top Kern point plus bottom Kern point. We're going to use these in our Kern point analysis, so we'll come back and look at this table again. Over here on the right, you can see based on the structural shape, we'll have different span to depth ratios. So this table would help you, if you get your first preliminary structural shape, you could come and determine an approximate depth you would need for that structural shape based on your span length, using these ratios. On the next couple slides, I'm going to go through some resources that are available in the PCI Design Handbook. So the PCI Design Handbook is a very useful handbook for pre-stressed and precast building design. So these are some load tables that are available for your preliminary design. And these tables include general section properties for these standardized sections. So they include section properties with no topping and then with standard topping depths. So here with a 2-inch cast in place topping that's applied in the field. They also give you some safe superimposed service loads and approximate cambers based on your span length and based on the location of your strands and the properties of strands. So your number of strands, the diameter of the strands, and whether the strands are straight or draped or harped. So here's a zoomed in view of the section geometry and standard properties that are available at the top of these load tables. So you can see you're given the area, moment of inertia, the distance between the bottom and the centroid and the top and the centroid of the section, your section modulus, so your I divided by Y for bottom and top, your standard weight for the section, the dead load, so additional superimposed dead load on the structure, and then also of volume to surface area ratio. So you can use these in the design process for the standard section. You can also see some standard material properties for the sections that the design aids were, or the load tables were developed based on. So here we have an F prime C of 5 KSI. We're using 270 KSI strands and half-inch diameter strands. On the next couple slides, I'm giving you just a quick overview of some of the assumptions that went into these load tables. Again, the load tables generally should just be used as a preliminary design aid, and you should, at the end, after you've selected your cross section and selected your strand, or the number of strands, your strand size, and the location of your strands, you should go back and analyze your actual section. But anyway, so some of the assumptions that went in. We have some assumptions on our safe superimposed loads. So these loads are your loading for the design aids should be all uniform service level loads across the entire surface. So the tables don't take into account any point loads. Loads in addition to the self-weight of the beam and topping. So the superimposed service load doesn't include self-weight and the topping, but any additional load on top of that. Service loads should include both live load and superimposed dead loads, and the tables assume that 10 pounds per square foot of the service load is superimposed dead load for untopped components, and 15 pounds per square foot is superimposed dead load for topped components. So these are some of the assumptions here for our superimposed loads. The load tables are based on, the load tables and the superimposed load and strand placement is based on an ultimate strength analysis. So they ensure that there's sufficient ultimate flexural strength. Also all the service limit checks, so all of our stress checks are satisfied. And also the shear design is checked with these load tables. Also, the camber and deflections that are reported are calculated using the PCI multiplier approach. The concrete strength is 5 KSI for the beams and 3 KSI for the toppings, 3.5 KSI at release, and the normal weight and lightweight densities are shown here as 150 pounds per cubic foot and 115 pounds per cubic foot. Losses are all calculated using the PCI pre-stress loss estimate procedure. And the strand location, I guess approximate values are shown in the tables, but the actual strand patterns are based on the region and also specific precast plants. So whenever you're designing these members, you should always coordinate with your precast plant to make sure that you have the exact strand locations for your design. So with these tables, you can come with your superimposed service load and your span length, and you can determine what cell you should be in. So if you have a 50-foot span with an 78 pounds per square foot superimposed service load, we'd be right here, and we can come over and determine our strand location and strand pattern. The strand location is specified in, with this designation. So the first number here tells us how many strands. So here we have 6 strands, 8 strands, 10 strands, 12 strands, 12 and 14 strands. The next number here tells us the size of the strands. So it's the here it's 8 divided by 16-inch diameter strands. So here we have all half-inch diameter strands for this load table. The last letter here tells us whether we have straight or depressed or harped strands. So you can see we have straight strands for the first 4 cases here, and then depressed or harped strands with a single harping point at the end here for the last 2 rows. Next we have the location of the strands. So you can see the end location and center location are given in these tables. So you can see when we have straight strands, the end and center locations are the same. When we have depressed or harped or draped strands, the location of the strand at the end is higher in the section than at midspan. Finally, the 3 numbers that are shown under the span length here in each row designate the superimposed service load that the beam can safely hold. So here for a 58-foot span length in this first row, the beam can safely hold 31 pounds per square foot. So this includes 10 pounds per square foot superimposed dead load and 21 pounds per square foot live load. The next number tells us the camber at erection, which here we see as 0.6 inches. And the last number is our long-term camber, which here is 0.1 inches. So we can use these values in our preliminary design. As I had mentioned, there are different standardized sections for bridges. The standard section that's used for bridges is very regionally dependent. So some regions will use more box beams, some regions won't allow box beams, some regions use AASHTO I-beams for shorter span bridges, or solid slab beams are sometimes used. And then also for longer spans, we have some type of bulb T section, but the specific geometry of that bulb T is dependent on state or region. And then there are also different pre-decked bulb T cross sections that are available in some regions. Another beam shape that's somewhat popular is this next D beam or next beam, which is kind of a stocky double T section that can either be pre-topped or require a cast-in-place top. That's used in New England and in the Northeast, but is being used in other parts of the country as well. And then there are U-beam sections, which is another voided member. So a slab is cast on top of these U-beams, which allows for a void in the center that are used for longer spans. So here, this one in Texas. And also these U-beams can be curved. So Florida and Colorado and some other states are looking at or have constructed bridges with curved U-beams. Shown here is a sample design aid for box beams. You can see you can use the first design aid here to figure out what cross section you might need. So based on your span length and your beam spacing, you can figure out what cross section you would want. So if you have spread box beams or adjacent box beams, you can figure out what cross section to start with. You can come here and with your span length, you can figure out what or how many strands you need if they're 6/10 diameter strands. So if we have a 70-foot span, we would need somewhere between 10 and 14 strands depending on what section we have. This design aid also has the basic section properties you'll need in your design. So your gross area, your distance from the bottom of the section to the centroid of your gross section, and your gross moment of inertia, and also your standard weight for the section. So here given in kips per foot. So these are from the PCI Bridge Design Manual, and the Bridge Design Manual has design aids like this for several of the standardized shapes that I showed on the previous slide. As I had mentioned, many regions and states will also have standard sections. So shown here are some of the standard sections that have been used and that are being used in Florida by the Florida Department of Transportation. So the two main sections that are used are these Florida I-beam sections, which is a bulb T section, and then also the Florida slab beams are being used. So you can see that these two are kind of the currently used standard sections. Some other sections that have been used are these Florida U-beams, Florida double T sections, and the Florida inverted T, which would require a cast-in-place deck on top here to complete the section. Normally, if a state has standardized sections, they'll also have resources where you can find the standard section properties for those standard sections. So here you can see the standard section properties for all of the Florida I-beams, from the 36-inch deep FIB to the 96-inch deep FIB. And you can see the area, the perimeter, moment of inertia about the X and Y axis, and then the distance between the bottom and the bottom in the centroid and the top in the centroid of the section. So you can use these. These are gross section properties for just the section itself, and you can use these in design. So different states will also have additional design aids. So FDOT also has a design aid to help you choose your initial section based on your beam spacing and your maximum beam span. So here you can see if we had a 100-foot span and a 6-foot beam spacing, then we could use an FIB 36 for our design. So you can see as you get wider spacing, your span lengths decrease for the sections. And you can also see for shorter span bridges here in Florida for FDOT, they recommend using this AASHTO Type 2 eye girder. So anyway, this is a way that you can preliminarily select your cross section. Cross sections will also have an available strand location. So here you can see a sample available strand location for the Florida I-beam. So here the first row of strands is 3 inches from the bottom, and then the strands are on a 2-inch by 2-inch grid. So typically this 2-inch by 2-inch grid is, I guess the 2-inch by 2-inch grid is kind of a standard grid for pre-stressed members. So just kind of the starting point of the grid and the number of available spaces in the width kind of vary by section. So you can see here we have 16 spaces at 2 inches for the first 2 rows, and then it decreases for each row above the first 2. So again, we would use this to lay out where we would want our strands in our design. Many states also have standard plans for their standardized sections. So shown here are some sample standard plans for the Florida I-beam sections. So you can see they have standard spacing and location for all the transverse reinforcement, the spalling reinforcement and confining or bursting reinforcement at the end region and then along the length of the section. And these standardized design or standard details satisfy most normal designs. We're next going to go through a Kern point analysis. The Kern point analysis allows us to develop a range, so a top Kern point and a bottom Kern point, where if we place a strand between these 2 points, we'll get 0 tension in the concrete face. So our bottom Kern point will prevent tension in the top, and the top Kern point will prevent tension in the bottom. On the following slides, I'm going to go through a derivation for the different expressions that are going to be useful in design based on our Kern point analysis. So essentially, we're going to look at a pre-stressing force that's applied at some eccentricity, And we're going to see when as we increase that eccentricity, we're going to decrease the compression in the top face until we finally get zero compression in that top face, or zero stresses in the top face. So essentially, when the eccentricity produces zero stress in the top face, we consider that our bottom Kern point. To find our bottom Kern point, we can just use our force in the tendon analysis, and we can find our my over I, our flexural stresses, minus P over A, so adding in our axial stresses, and set it equal to 0 to get zero stress in the top fiber. Our moment here, we're going to assume that we have no externally applied load, so no external moment. So our only moment is from the eccentricity of our strands, which is P times our eccentricity E. So we can set this equal to 0, plugging in our P times E, and then solve for our eccentricity, which we're saying is our bottom Kern point. And we can see our bottom Kern point then is just equal to our section modulus S sub T divided by A. So this is our bottom Kern point equation that we'll use moving forward. We can do the same thing with an eccentricity above our centroid of the section to find our top Kern point. So again here, we're setting our bottom fiber stress equal to 0, and we can substitute in our section modulus. And then we can solve for our eccentricity, and this will give us a top Kern point equal to our section modulus S sub B divided by A. So we'll use this top Kern points moving forward. With our top and bottom Kern point, we now have a range where if we keep the centroid or the line of action of our pre-stressing between our top and bottom Kern point, we'll have zero tension in either the top or bottom face of our section. So anyway, this again, the derivation was based on no external applied moment and no tension permitted in the section. We can modify the above expression to include both pre-stressing and externally applied moments. So here again, we'll have our moment applied, and we can we have our applied moment and our pre-stressing applied at some eccentricity. So this would be equal to an axial load or P applied at a different eccentricity. So we can come up with an equivalent E prime that would account for both the strand eccentricity and the externally applied moment. So again, if we want no tension in the top face, then we would need to keep this E prime less than our bottom Kern point. So if we set our top fiber stress equal to 0, we'll have our flexural stresses from our strand eccentricity, P times E, and then we'll also have our flexural stresses from our externally applied load, My over I, and then our axial stress, P over A, equal to 0. So we can simplify the expression and solve for our KB component here. So we have our eccentricity minus our live load moment divided by P needs to be less than our KB. Using these expressions, we can calculate or come up with an equation for the maximum pre-stressing that's allowed to keep our top stresses below 0. So you can see if we need to keep our actual pre-stressing force less than our P max equal to our live load divided by E minus KB. And then we can also do the same thing for tension in the bottom face to come up with a minimum pre-stressing required for no tension to be in the bottom face. So here we need a pre-stressing that's greater than or equal to our P min, which is equal to our live load divided by E plus KT. So we can use these equations in our design process. If we're looking at the initial conditions and self-weight only, so if we want to keep tension at, out of the top face, then we would want our E to be less than or equal to KB plus M min divided by P sub I, or our initial pre-stressing force. So this is one equation that we'll use to come up with our eccentricity. And remember, typically the top, or the tension in the top is going to control at release. So that's why we're looking at our M min and our P sub I. Tension in the bottom of our section is typically going to control at service. So because of that, for our bottom Kern point, or bottom fiber expression, our top Kern point expression, we would use our final conditions. So we'd use the force in the pre-stressing after all losses, or P sub F, and we'd use the maximum moment due to all of our service loads. So our self-weight, our superimposed dead load, and our live loads. And we can use this expression then to estimate the pre-stressing that we need to have. So the minimum pre-stressing that we can have. So for design, we're going to use this PF expression, and we're going to use an approximate value for the E plus KT. We can estimate E plus KT based on these tables from Collins and Mitchell. So you can see, based on what section we have, we can estimate an E plus KT. So if we have a double T section, one standard section for buildings, our E plus KT for the design, we could use 0.7H. So we'd use 0.7H as the denominator in the equation on the previous slide. Another expression that may be useful during the design process is if we combine the two relationships and eliminate our eccentricity E. So you can see here the PF times KT plus KB needs to be greater than or equal to M max minus PF over PI times M min. So we can use this to select the smallest PF that will satisfy our design limits. So the derivation on the last couple slides has all been without tension being allowed in the top or bottom face. We can modify these expressions to include tension. So here what I'm doing is adding in a tension limit rather than having our stress in the top fiber equal to 0. We make sure that it's less than or equal to some tension limit. So we can add in these limits. So if we're looking at the top fiber stresses, typically top fiber stresses control at release. So we can add in our release stress limits. So here at the end region and elsewhere, we have our stress limits from ACI 318-19. And here we're looking at our stresses in our bottom fiber or bottom face, and these are typically these typically control at service. So our stress limit that we would add in is our stress limit at service, which is 7.5 times the square root of F prime C in ACI. So we can solve from this expression. We can solve for either the pre-stress force limit. So come up with the minimum amount of pre-stressing that we can have to satisfy our initial design. And we can also come up with an equation to find the minimum eccentricity of our strands, so E min. So shown here are how we can use these Kern point equations in our actual design procedure. So we would use the Kern point equations here to select our smallest possible pre-stressing force in service, so either with or without tensile stresses being allowed. We can then come up with a range of eccentricities that we need to keep our strands between. Again, without or with tension, stress is allowed. We'd find a minimum and maximum eccentricity at the end and at the midspan, and then keep our actual strand eccentricity between these values. And then we would detail accordingly. So if we have no tension permitted, then we'd have a minimum and a maximum eccentricity, where we would need to keep our strand profile between these Kern points. If we have tension permitted, then you can see that our Kern point range expands. So now we have this range where we can put our pre-stressing strands between these 2 points. So if possible, we want a straight strand profile. So you can see here with tension permitted, we may just be able to get a straight strand profile between our 2 limits. On the next couple slides, I'm going to go through just a general design procedure. The first step, again, you need to choose your cross-section type. This is going to be dependent on your span length and loading and the availability of local precasters. You can use some of the design guides that I showed earlier in this presentation to select the initial cross-section. And you can also remember some of these span to depth ratio and approximate span length rules of thumb. You will need to assume initially a release concrete strength F prime CI and ultimate strength F prime C. And for buildings, 3.5 KSI release and 5 KSI for ultimate is a good starting point. When doing bridge design, these values are typically going to be a little higher and can be as high as 6.5 KSI for release and 10, 12 KSI for ultimate. The next step is to choose the amount of pre-stressing that you'll need. You can either use a design aid if it's available to figure out the required strand area or number of strands for your given span and loading. Or you can use the Kern point analysis that we looked at earlier in this presentation. If you're using the Kern point analysis, the first thing you would need to do is determine your approximate E plus KT from the below tables. Again, these are design expressions, so if you have a cross-section that's different than any of the cross-sections shown, you should pick an E plus KT that's closest to one of these cross-sections. So pick one of these that's closest to the shape you're actually analyzing and then use the E plus KT for that section. We can then use our Kern point expression to figure out the minimum amount of pre-stressing that we'll need to satisfy some of these Kern point expressions. So here, solving for our area of pre-stressing, you can see we need to keep our area pre-stressing greater than this value here with our maximum service moment and our final pre-stressing force and the allowable tensile stress in the bottom fiber, which in ACI 318-19 is 7.5 times the square root of F prime C. So we can use this to select the minimum number of strands required to satisfy this value. Then we can check our approximate moment capacity, just approximating the lever arm here as 0.9H to make sure that a rough estimate of our moment capacity will meet our ultimate moment requirement. Next, we need to choose our tendon profile. We can choose our tendon profile based on our minimum and maximum eccentricities that are allowed from our Kern point expressions. So we would find an E-min and E-max at the transfer length and also at midspan of our section. And then we would try to keep our actual tendon profile between those limits. The actual location of our strands would be based on the available pre-stressing grid for the section. So we can only lay out this, or we can only put a strand, in an available strand location. So we would need to talk to our local precaster or look at our design aids or design guides to be able to see where we can put strands. And then finally here we would draw our actual cross section with the actual strand locations. And then we would transition from the design phase of our design to the analysis phase of our design process. At this point, we're transitioning from our design phase of the design process to the analysis phase of the design process. And the first thing we need to do in the analysis phase is check the actual concrete stresses in our actual section, in our actual beam. So looking at the actual section, we can use the force in the tendon approach, or we'll typically use force in the tendon, although we could use another procedure like strain compatibility or a software to estimate stresses. And typically we'll need to check at release, and then we'll also need to check our stresses due to both sustained and service loads. So at release, typically tension in the top of our section at the ends and at midspan will control, or compression at the ends of our member may control. So these are the kind of the three that we would primarily need to check, although we are responsible for meeting our stress checks along the whole length of the beam. So yeah. At service, typically our tensile stress on the bottom of the beam is going to control, both due to our sustained loads and service loads. Although there is a limit on the sustained compression stress in the section, which may be at the top of the beam at midspan. We can next check our flexural capacity. So we need to calculate the actual moment capacity of our section. And if we have harped or draped strands, we need to calculate the ultimate capacity at several different points along the length of the beam. So here we can use either our ACI or AASHTO expressions to calculate our strand stress, or we can use the strain compatibility approach to find our strand stress and our nominal moment. So here I show the ACI expressions for a fully pre-stressed section. So we could calculate our strand stress, our compression block depth, and our factored nominal moment. Our phi factor here, we would need to calculate the strain in our pre-stressing caused by the applied moment and determine whether that's greater than, equal to, or less than 0.005. As long as we're greater than 0.005, then we're tension controlled, so our phi is 0.9. And anyway, we would need to make sure that our phi mn is greater than or equal to mu. If our phi mn was less than mu, we would need to go back and modify our design by either increasing our number of strands, increasing our eccentricity, or modifying our section and choosing another section. As I mentioned on the previous slide, we need to check to see if our section is tension controlled. To do that, we need to find the strain at the centroid of our pre-stressing. So we can calculate that assuming a linear strain profile and top fiber stress of 0.003. And then we can compare the strain in our pre-stressing to our different limits. If we're greater than or equal to 0.005, then we'll be tension controlled, and we can use a phi factor of 0.9. This is typically going to be the case for our pre-stress sections with steel reinforcing or with steel pre-stressing. The next thing that we need to do is we need to check the reserve strength after cracking in our section. We want to make sure that our section doesn't crack and immediately fail. Cracking gives or makes us aware that the beam is approaching failure. So we want to make sure that when it cracks, we have some ductility and some additional capacity in the beam. So ACI requires that our phi mn over m cracking be greater than 1.2. So we want 20% additional strength in our section after cracking before failure. So to calculate this, we need to find our M cracking. So I'm giving you one way that you can find it. You can solve for it directly using this M cracking expression, using the pre-stressing force after all losses. So again, we would check this limit, and if the limit doesn't check, we would need to go back and modify our design. Next, we would need to check our deflections. So here is the table from ACI 31819 with our different deflection limits. You can see the deflections are based on member type, condition, whether you're supporting or not supporting non-structural elements. And then based on these, it tells you what deflection or what loads to include when considering your deflections, and then the different deflection limits. Typically, our deflections will be limited based on these two limits. So our final deflections caused by all applied loads after the attachment of non-structural elements needs to be less than L over 240. So our deflection due to superimposed dead loads and live loads needs to be less than 240. And then our immediate deflections from live loads needs to be less than L over 360. So these are the two limits on from the previous table that will typically be important for us. At this point, you can pause this presentation and go to example 1, where we design a beam to span 46 feet with the given parameters. Example 2 is a full design of an untopped beam to span 70 feet with the given parameters. If a structural system's designed to have a deck or cast-in-place topping that's made composite with the pre-stressed member, we're going to need both non-composite and composite section properties for the design process. So on the next couple slides, I'm going to show you or talk about the composite section properties and when they should be used. For composite section properties, we're going to need to use the effective flange width for our section. So in ACI, there's a set of equations to calculate the effective flange width. So you would go to ACI 31819 to calculate your effective flange width. For AASHTO, there's a separate requirement. So AASHTO allows the effective flange width to be taken as just the tributary width perpendicular to the axis of the member. For determining, I guess the effective flange width here. So this is going to typically just be your beam spacing. So if you have a 4 foot, 6 foot, 8 foot, 10 foot beam spacing, that'll be the effective width of your top flange here of your deck in bridge design. The composite section properties can be found based on the properties of your deck and the properties of your precast section. So we would find first the area, moment of inertia, and stiffness of the deck, or then modulus of elasticity of the deck, and the same for our precast section. Then we would find a modular ratio relating the modulus of the deck concrete to the modulus of the beam concrete. And we would transform our deck concrete into an equivalent kind of area of beam concrete to get our composite section. On this slide, I'm showing you the equations where you can find the area of our deck, if it's just a regular rectangular deck, the moment of inertia of the deck, and then also our Y of the deck from the bottom. So we need to find the distance between the bottom of our section and the centroid of the deck. So we can use this expression here. We also have our modular ratio, which is just the ratio of our modulus of elasticity of our deck concrete to the modulus of elasticity of our concrete in the precast section. Typically, we'll be given the cross-sectional properties for our precast section So, we'll just be given our AG and our IG and our YG for our precast section. So that's why I'm not showing them here. So using our gross properties for our deck and our precast section, we can combine them to calculate our composite section properties using these expressions. So our height is just the height of the precast section plus the height of the deck. The area of our concrete is just the area of our precast section plus the transformed area of the deck. And the centroid between the bottom and or the distance between the bottom and the centroid of the composite section, again, we just take the area of our gross section times the distance between the bottom and the centroid of our gross section plus the transformed area of our deck times the distance between the bottom and the centroid of our deck divided by our total composite area. Then our composite moment of inertia is we can use parallel axis theorem. So I of our gross section plus AD squared for our gross section component plus I, transformed I of our deck plus AD squared for our deck, where we transform our deck area. So we can use these equations to calculate our composite section properties. I want to note that these are the gross non-composite and composite section properties. We could also transform our steel and pre-stressing to calculate or to find short-term and long-term transformed non-composite and composite section properties. So I'm not going to do that here, but that's something that you can do for a more refined analysis. At this point, you can go to example 3, where I calculate composite section properties for the below Florida I-beam section that's shown here. Whether you use non-composite or composite section properties is dependent on the type of load being applied onto the structure. So at transfer, there's no deck on top of the beam, so we're going to use non-composite section properties with the release strength of our concrete. At time of construction, the deck is going to be there, but it's not going to be hardened, and so all the construction loads are just going to be resisted by the non-composite section, or just the beam itself. After the deck is allowed to harden and gain strength, then the deck's going to start to contribute to the strength of the structure. So we'll use composite section properties when the entire composite section is resisting the load. So an example is live loads. So the entire composite section is resisting the load of the truck or traffic. So again, at transfer, we're going to use our non-composite section properties with the pre-stressing force after transfer. So we can find our stresses due to pre-stressing and our stresses due to self-weight using our non-composite section. We don't have a deck there, so we don't include it. And we can use these to find the stresses in the top and bottom fiber of our precast section. At construction or time of deck placement, we're going to use our non-composite section properties with our pre-stressing force at time of deck placement. So we'll have our stresses from our pre-stressing. Again, we're using the final pre-stressing force or pre-stressing force at the time of deck placement, P sub F, plus the self-weight stresses, plus our deck stresses. So you can see we're having some additional stress that's applied from the weight of the deck, but at this point the deck is not contributing to the strength of the section. So at this point we would find the stresses at the top and bottom fiber of our precast section again. At service, we should use non-composite section properties for all of the stresses from our pre-stressing, self-weight moment, and deck moment. So all the stresses from before when the deck was cast, we'll still use non-composite section properties. And we'll use composite section properties for the stresses from our any applied loads after the deck concrete's hardened. So live loads and superimposed dead loads that are applied after the deck's hardened. So here we'll have our stresses from our previous construction stage, plus the stresses from our live load and superimposed dead load that's applied after the deck's hardened. And it'll give us our total stresses that are shown here. So here we would need to find the stresses in the bottom fiber of our precast section, the top fiber of our precast section, and then also the bottom and top fiber of our deck. You can see there's a discontinuity in our stress diagram because our loads are applied at different times in the section. So that concludes our lecture here on the design for Flexure for prestressed concrete members.